Alrighty guys, we're going to go ahead and get started with our Coulombs Law homework. I want to go over a few problems. So first thing you're going to notice is that on this page, I give you a bunch of information up here. I tell you what Coulombs Law is. I tell you what the K value is in Coulombs Law, that constant. I tell you the charge on an electron, proton, and neutron, and then the mass of an electron, proton, and neutron. So first thing I want to do is look at this problem. It says a piggy bank holds 35,000 nickels. FYI, nickels have a mass of 6 grams. How many cents does the piggy bank hold? So this problem doesn't have to do with protons, electrons, or neutrons, but it does have to do with conversion. And in case you forgot, I want to show you how to do that really quick. So if we have 35,000 nickels, we're going to say we have 35,000 nickels times, and we want to figure out how many cents this piggy bank has. Well, in order to do that, we need to figure out how many cents is 1 nickel. Well, 1 nickel is equal to 5 cents. So if I set up a conversion or a ratio here, I'm going to have 5 cents on top because every 1 nickel is worth 5 cents. This way, when I multiply through, I have nickels on top here, nickels on the bottom there, they cancel out, and I'm just left with cents. So this would tell me that 35,000 nickels is equal to 175,000 cents. Now let's take a look at what the mass of these nickels are. So again, I have 35,000 nickels. And I know in my problem, it tells me right here that nickels have a mass of 6 grams. So that means that 1 nickel is equal to 6 grams. So if I set up a ratio like I did before, I would put the mass on top and the nickel on the bottom. This way nickels cancel out again, and I just multiply through. 35,000 times 6, that's going to give me 210,000 grams. And that's it, right? When we are setting up these ratios and these equations, we want to make sure that whatever's on top here, so in this case nickels, is going to be on the bottom here. Whatever's on top here, nickels, is on the bottom here. Now let's take a look at this with electrons and protons. Number 2 says after rubbing the gray strip with paper, it has 35,000 extra electrons on it. How many coulombs of charge are on the gray strip? So let's set this up as before. We know that we have 35,000 electrons. I'm going to abbreviate electrons with E minus. And we want to figure out how many coulombs of charge they have. Well, in order to do that, we first need to know how much charge does 1 electron have. Well, if I look at my table above, it's going to show me that 1 electron has a charge of negative 1.6 times 10 to the negative 19. So I'm going to write that down here, negative 1.6. And instead of times 10, I'm going to write E, which means the same thing, negative 19 coulombs. Now, when I set up my ratio, I have electrons on the top here. That means I need electrons on the bottom here, which means on top, I need the coulombs of charge. Negative 1.6 e to the negative 19. Electrons cancels out with electrons. I just multiply through. I figure out that 35,000 electrons has a charge of negative 5.6 e to the negative 15th coulombs. Now we want to figure out what the mass of these electrons are. So to do that, we're going to need to take the number of electrons like we had before, 35,000, and we also want to figure out the mass of 1 electron. So 1 electron is going to have what kind of mass? Well, if we look back at our table up here, we're going to see that the mass of 1 electron is 9.11 times 10 to the negative 31st. And this mass is given to us in kilograms, because that's the units of mass in physics. So we set up our ratio like before. We put 1 electron on the bottom, and then we put our mass on top. 9.11 e to the negative 31st kilograms. We see that electrons cancel out like before, and we just multiply through. We find out that the mass of these electrons is 3.19 e to the negative 26 kilograms. And we know that this answer is correct because this mass is very, very small. All right, let's take a look at number 4 here. Number 4 says, after rubbing your socks on the carpet, they gain -3 times 10 to the -7th coulombs of extra electrons. So the reason it's negative is because it's talking about the charge here. Coulombs is in regards to charge. So first thing it wants us to do is figure out how many extra electrons got onto your socks. So if it's talking about coulombs here, which we said our charge, we're probably going to need our number that deals with coulombs of charge right here. And this is telling us that 1 electron is equal to -1.6 times 10 to the -19th coulombs. So if I set up my equation, I have -3 e to the -7th coulombs times, well, I have coulombs on top here, I need coulombs on the bottom here. And that means I'm going to have -1.6 e to the -19th coulombs. And that's just this number right here, which is telling me that 1 electron, which I'm going to put on top, is equal to -1.6 times 10 to the -19th coulombs of charge. Now my coulombs cancel out, I multiply through, and I find out that I have 1.875 e to the 12th electrons. Let's take a look at letter B. What is the mass of these extra electrons? So since it's talking about electrons here, that means I'm going to have to use my answer above to solve for the mass here. Because I don't have any conversion from charge to mass. I only have a conversion from electrons to charge and electrons to mass. So 1.875 e to the 12th electrons. And I know that 1 electron has the mass of 9.11 times 10 to the -31st kilograms. I have electrons on top here, which means I need electrons on the bottom here, which means mass is going to go on top. 9.11 e to the -31st kilograms. My electrons cancel out, I multiply through, just like I've been doing, and I find out that these electrons have a mass of 1.71 e to the -18th kilograms. Again, this mass is very small, which is what I would expect because I'm dealing with electrons and they have very tiny masses. Even though I have a bunch of electrons here, it doesn't matter because the mass of 1 electron is so small that I'm still going to have an overall very tiny mass. Let's take a look at number 2 here, and number 2 says a negative charge of -4 times 10 to the -6 coulombs and a positive charge of 7 times 10 to the -6 coulombs are separated by a distance 0.15 meters. What is the electrostatic force between them? Is this repulsive or attractive? So I'm going to start off with drawing a picture here. And here's my first charge. I'm going to say it's Q1. And I know that it's separated by a distance. And it tells me that distance is 0.15 meters. And here's my second charge, Q2. Now let's go ahead and label what these charges are and what our variables are. First, I'm going to start with force. And in the problem, it's telling me what is the force. So that means that I don't know the force. Next, I have Q1, which is my first charge. And I'm just going to say that that's the first charge that they mention here. So that's -4 e to the -6 coulombs. Next, we'll do charge 2, and that's the second charge they mentioned. That's going to be positive 7 e to the -6 coulombs. Then we're going to have distance, and the distance that they're separated by is 0.15 meters. And then lastly, in our Coulombs Law equation, which is just right here, we have the letter K, and K is always a constant, so K is always 9e9, and we can see that down here, 9 times 10 to the 9th. Now that I have all my information, I can go ahead and solve. If I write my equation, I have force equals K, Q1, Q2, all over d squared. So if I plug my values in, I still have force because that's unknown. K is 9e9 times Q1, -4 e to the -6, Q2, 7 e to the -6 over d squared, 0.15 squared. All you have to do is plug this in your calculator and you end up with a force that should be equal to -11.2 newtons. We notice that this force is negative, and we also saw here that one of our charges was negative and the other charge is positive, meaning that they are going to attract each other. Let's take a look at number 4 now. Number 4 says 2 negative charges negative 1.5 coulombs and negative 0.175 coulombs push each other with a repulsive force of 19.2 newtons. How far apart are these charges? So let's go ahead and draw the picture just like we did before. So here's Q1, and it's some distance apart, and here's Q2. All these pictures are going to look the same. They're just going to look like kind of dumbbells, right, or barbells, where we have one charge over here separated by some distance and another charge there. So let's identify what our variables are. So the force is 19.2 newtons. Charge 1 is going to be negative 1.5 coulombs. Charge 2 is going to be negative 0.75 coulombs. The distance between them is unknown, and the K value is always 9E9. So if we look at our equation, we know that force is equal to K times Q1 times Q2 all over D squared. But in this equation, we're trying to solve for how far apart these two charges are. So there's two ways to approach this. The first way is we can just plug all of our numbers in, simplify, and then move some things around. Or we can move some things around first and then plug the numbers in. Let's do the second one, where we move some things around first and then put our numbers in, so it's a lot easier to solve. So we're solving for D, so let's get D by itself. I'm going to multiply D over to the other side. That gives me D squared times F is equal to K Q1 Q2. Next, I'm going to divide by F, so I get D by itself. So that's going to give me D squared is equal to K Q1 Q2 all over F. Again, I'm solving for D, not D squared, so I'm just going to square root both sides. That means that our final equation is just D equals the square root of K times Q1 times Q2 all over F. And all of this is under our square root. All we have to do now is plug our numbers in. So we have D is equal to the square root of K, which we said was 9E9, times Q1, which is negative 1.5, times Q2, which is negative 0.75, all divided by our force, which is 19.2. Once we plug all that in our calculator, we should end up with our final distance between them, which should be 2.3 e to the 4th meters. All right, let's take a look at our last Coulombs Law problem. And this one is talking about a negative charge of negative 0.0005 coulombs exerts an attractive force of negative 9 newtons on a second charge that is 0.8 meters away. So if we draw our picture just like before, and we know our pictures just look the same, we have Q1, we have Q2. This time though, we don't know the charge of Q2, and the distance between them is 0.8. So let's list our variables. F, well, F is the force between them, and that's negative 9 newtons. Q1 is our first charge, and that's negative 0.0005 coulombs. Q2 is our second charge, and that one's unknown at the moment. We don't have any idea what it is. It didn't tell us in our problem. Next, we have D, the distance between them, and that's 0.8. And then lastly, we have K, which is a constant, which is always 9E9. Now we want to write our equation. F equals K, Q1, Q2, all over D squared. So we just talked about in the last problem that we have two ways to do this. One way we can just plug all of our numbers in, simplify and solve, or the other way is that we can manipulate our equation to solve for Q first and then plug our numbers in. So let's do that way again, where we manipulate the equation to solve for Q. So we need to get Q2 by itself, which means we should multiply D squared over. So that means F times D squared is equal to K times Q1 times Q2. Now, since we need Q2 by itself, we're going to divide by K and Q1 on both sides. Doing so is going to get rid of K and Q1 on the right, which is just going to leave us with Q2 is equal to force times distance squared, all divided by K times Q1. So all we have to do now is plug our numbers in. Force is negative 9. D is 0.8, and then we have to square it, don't forget. Then divided by K, which is 9E9, times Q1, which is negative 0.0005. Once we simplify, we find out that the charge between these two objects should be equal to 1.28 e to the negative 6 coulombs. And it makes sense because we got a positive number here. We would expect a positive number because our charge 1 was negative, and we know that the force between them is attractive. All right, guys, we have made it to the end, but this is the most difficult part. This one says, directions for the following problems determine the new force quantity between the charges when one or more of the values is changed. So in order to do that, we really need to understand our equation up here. And in Coulombs law, we have force is equal to K times Q1, Q2 over distance squared. And what does that mean? Well, since charge is on top and there's only one charge, it's not charge squared. That just means that whatever we increase or decrease our charge by, as long as we're keeping the distance and the other charge constant, our force is going to increase by the same amount. So in other words, Q1 increases, force is going to increase. Q1 decreases, force is going to decrease. All right, so whatever we do to Q1 or whatever we do to one charge is going to happen to our force, as long as everything else is kept constant. So if we take a look at number 1 here, it says two charge objects with a repulsive force of 10 newtons. If the charge of one object is doubled, what's the new force? Well, we just said whatever we do to charge is going to happen to force. So if we double the charge, we're going to double the force. So 10 doubled, that just means 10 times 2. That means that our new force is 20 newtons. Number 2, two charged objects have a repulsive force of 10 newtons. If the charge of both objects is doubled, then what is the new force? Well, let's just do what we did above. 10 times 2 for our one charge, right? Because if we double one charge, it's going to double the force. But we're doubling two charges, so we're going to do this again. 10 times 2. That means that our force is now going to be 40 newtons. It's going to be 4 times as big. And that's because we doubled both of our charges. Two charged objects have a repulsive force of 10 newtons. If the charge of one of the objects is halved, what's going to happen? Well, whatever we do to one of our charges, we're going to do to our force. So we cut our charge in half, we're going to cut our force in half. So now our force is going to be 5 newtons. Two charged objects have a repulsive force of 10 newtons. If the charge of one object is quartered, what's going to happen? Again, whatever we do to our charge, we're going to do to our force. So quartered means 1/4, so times 1/4, that means that our force is now 2.5 newtons. It's quartered. Now let's take a look at distance. This is definitely the harder one. How is manipulating distance going to change our force? Well, let's look at our equation. We notice that force is up here, but distance is now on the bottom, and it's squared, which really means that if we're keeping everything else constant, force is just equal to 1 over distance squared. So what does that mean? That means that whatever we do to distance is really going to impact force, but how so? Well, since distance is on the bottom, it's going to have the opposite effect. And since it's squared, it's going to have the opposite effect squared. So let's walk through some of these so we can really see it. But I'll just write that little equation over here. F is equal to 1 over d squared. So this is just telling us that if distance increases, force is going to decrease, but it's going to decrease by a squared amount, right? And then if distance decreases, force is going to increase, and again, it's going to be by a squared amount. And we'll see that in our problem right now. Two charged objects have a repulsive force of 10 newtons. If the distance separating the objects is doubled, what is the new force? So if it's doubled, meaning that distance is getting bigger, we should expect the force to get smaller. And the force is going to get smaller by a squared amount. So if we plug this into our simplified equation that we made over here, just by saying that everything else was kept constant, that would be 1 over, well, d is now double, so it would be 2. But wait, it's squared. So force should be equal to 1/4, meaning that the force will be quartered. So 10 times 1/4, that's going to give us 2.5 newtons. And that makes sense because we would expect as the distance increases, our force to decrease. Two charged objects have a repulsive force of 10 newtons. If the distance separating the objects is tripled, then what is the new force? Same thing. Force is equal to 1 over the distance squared. So in this case, 3 squared, 1/9. So 10 times 1/9, that just gives us 10 nines. Two objects have a repulsive force of 10 newtons. If the distance separating the objects is quadrupled, then what is the new force? So distance is quadrupled, meaning that it's getting bigger. So we would expect a smaller force, 1 over 4 squared. That means 10 times 1 over 16. That's going to give us 5/8. It's an ugly looking 8. It almost looks like a 6. Now we have a different type of problem where instead of this time our distance getting bigger, it's going to get smaller. Two charged objects have a repulsive force of 10 newtons. If the distance separating the object is halved, then what is the new force? So F is equal to 1 over, and we said distance squared, but distance is halved. So it's really 0.5 and it's squared. So this is the part that I recommend some of you guys use your calculator for, because 1 over 0.5 squared is 4, meaning that our force is going to be 4 times as big. And again, use your calculator if you're unsure on how I did that math, but very simply, right, 1 over 0.5 squared is just 1 over 0.25, and 1 over 0.25 is just 1 over 1/4. This goes on top, which just leaves us with 4 times as big. And that's it for our homework, all right? The takeaway here is that when we manipulate our equation and we want to figure out what happens when we change just charge or just distance, we need to remember that force and distance have an inverse square relationship, meaning as distance increases, force is going to decrease squared. As distance decreases, force is going to increase squared. At the very least, you just got to remember that when we increase our distance, we're going to feel less force. And when we decrease our distance, meaning that these charges get closer together, they're going to feel more force. And then on the opposite end, when we talk about charge and force are directly related. The bigger the charge, the more force. The smaller the charge, the less force.